Hello everyone. Today we start the next lecture of the nonlinear programming problem. Okay, so in this lecture we do some questions regarding Lagrangian multiplier method. Okay, so let us start. Using Lagrangian multiplier method, solve the NLPP, you can say nonlinear programming problem. So it is given that minimize of z equals x1 square plus x2 square plus x3 square and subject to the condition for x1 plus x2 square plus twice of x3 equal 40 and x1 x2 x3 is greater than 0. So you can see that here the decision variables are 3. Okay, and there is one constant. So first we can write like this. Okay, we can write this z as function of x1 x2 x3, so that is x1 square plus x2 square plus x3 square. And subject to the condition, we can write this one as function of x1, x2, x3, and that can be written as 4x1 plus x2 square plus twice of x3 minus 40. Okay, and we define the Lagrangian function, so it can be written as L function of x1, x2, x3 and lambda. So it can be written as x1 square plus x2 square plus x3 square minus lambda times this one for x1 plus x2 square plus 2x3 minus 40. Okay, so to find the necessary conditions, we find the partial derivative of L with respect to x1, x2, x3 and then lambda. Okay, so from here we obtain four equations as you can see here. So first we write for partial derivative of L with respect to x1. So you can see here if you do partial derivative with respect to x1, what you obtain here. This is twice of x1. This is 0, this is 0, it will be minus 4 lambda. Okay, so that's why we can write it. This is equal to 0, so from here we obtain x1 equals to twice of lambda. And if we calculate del L over del x2, then we obtain twice of x2 minus 2 lambda x2. This is equal to 0. So from this equation, you can see here, this can be written as 2 times x2 and this is 1 minus lambda. This is equal to 0. Okay. So from here, we can see that either x2 is 0 or lambda equal to 1. Okay. If we calculate partial derivative with respect to x3, then we obtained 2x3 minus 2 lambda equal to 0. So we obtained x3 equal to lambda. And when we do partial derivative with respect to lambda, then we obtained this. Okay, this becomes 0, this becomes 0, this becomes 0, and we obtain this. So now solving these equations, we have to calculate the values of x1, x2, x3 and lambda. Okay, so firstly, if we see from second equation, we have twice of x2 and 1 minus lambda equal to 0. So you can see 2 is greater than 0, so it means either x2 will be 0 or 1 minus lambda will be 0. So if x2 is 0, yeah, you can say lambda equal to 1. Okay, so if we take first case when x2 is 0, so we obtained, you can see if x2 is 0, so we can put the value of x2 in this equation. So from here we got 4x1 plus x3 equal to 40. You can put the value of x1 and x3 in terms of lambda. So we got this is 2 lambda, so this is 8 lambda plus, and this is lambda equal to 14. Okay, so from here we got lambda equal to 14 by 9. So we can solve it and we take 1.4. Okay, so now if we obtain the value of lambda, then we can easily find the value of x1 and x2. So from here we get the stream point x1 equal to 2.8, x2 is 0, and x3 1.4. And lambda is also 1.4. Now the case second when lambda is 1. Okay, then we need to calculate the value of x1, x2, x3. So from here we obtained x1 is 2, x3 is 1, and we can put the value of x1, x3 here, so we obtain the value of x2 here. Okay, so from here we obtained x2 equal to 2. So here we obtain two extreme points which are this one 2.80, 1.4 and 1.4 and 2211. So now we have to check that at which point the given function is minimum. Okay. So for this we calculate the folded Hessian matrix. So we can see here this is del H over del X1, del H over del X2. Okay. And del H over del X. Something is missing here. This one is 0. Okay. And this is del L over del X1, del H over del X2, and del H over del X. Now this is complete Bolden Hessian matrix. Okay. So now we put the values here. So we obtained this one. Okay. So first we calculate the value of this Bolden Hessian matrix at the first extreme point, which is 2.80 and 1.4, when lambda is 1.4. So just put the value of lambda and x2 here. So we obtained this one. So now we calculate the leading principal minor of this. Okay. So we obtained here D4 is 32, D3 is 12.8. Okay. So here all the principal minors are greater than 0 sign. Since the sign of D3 and D4 are same but not same as the sign of minus 1 to the power n equal to minus 1. So it means function has no local minima at this point. As we see in the previous lecture that for the local minimum we have this condition. Okay, but here this is not satisfied. So that's why the function has no local minima at this point. Now we check for second point, which is 2 to 1 and lambda equal to 1. So you can see here. Now we calculate the leading principal minor of a D4 and D3. So that will be, this is minus 64 and this is minus 32. Since the sign of D3 and D4 are same and which also same as the sign of minus 1 to the power m. So this is negative. So it means fx at local minima at the point 2, 2, 1. And at this point, the minimum value of z is none. Okay, so I think it is clear to you.